Good. Good morning, everybody. My name is Alban Farchi. I'm a researcher at École des Ponts in Paris, in Marc Bocquet's group. And today, what I will present is the result of a collaboration that we have with ECMWF on the topic of model error correction with neural networks. So I would like to start by a few reminders about weak constraint for D-VAR. So the idea of weak constraint for D-VAR is that we want to relax the perfect model assumptions that we have in strong constraint for D-VAR. And the price to pay for this is a huge increase in problem dimensionality. But fortunately, this can be mitigated if we make some additional assumptions. So for example, we can assume that the model error, W here, is constant over the window, and in such a way that the model evolution can be written using what I call the weak constraint model. So then you obtain a cost function which depends on the model error and the initial state. And you have three terms in this cost function. You have the background term, you have the observation error term, which depends on the weak constraint model, and you have this third term, which is the model error term. So this formulation is called forcing formulation of weak constraint for D-VAR, and this is what is used by ECMWF in OOPS, the data assimilation system. Okay, now suppose that you have a dynamical model that is parameterized by a set of parameters, P, that are still constant over the window. So your model evolution is written like this. And if you apply the same ideas, then you obtain a cost function which now depends on the model parameters and the initial state. And you have again three terms: background term, same as before, observation error term, which now depends on the parameterized model. And you have the model error term has been replaced by a sort of parameter error term. And now if you think of P as a set of parameters of a neural network, the weights and biases of this neural network, you can imagine that this approach is a sort of neural network formulation of weak constraint for D-VAR. So now what I would like to do is bring the two approaches together. So what I will do is I will assume that the model error is still constant over the window, but is estimated using a neural network. So this W is given by a neural network F. And actually, the model evolution, you can write it using the weak constraint model composed with the neural network. And this equation is very important because it means that all what we want to do can be based on the forcing formulation of weak constraint for D-VAR already implemented. So in the incremental assimilation framework that is implemented in OOPS, the most important thing is to be able to compute the gradient of the incremental cost function. And I won't go too much into details, but this is the pseudo algorithm that we use to compute this gradient. And everything which is in black is already in place for weak constraint for D-VAR. And if we want our new methods, we only need to implement the red lines. So we have here the tangent linear of the neural network, and here we have the adjoint of the neural network. Okay, quick recap. So we want to implement this, let's say, simplified neural network for D-VAR. We can reuse everything that we have for weak constraint for D-VAR, and we need to add a few bricks, a few ingredients. So we need the forward operator of the neural network if we want to compute the nonlinear trajectory at the start of each outer iteration. And then we need, for the gradient, we need the tangent linear and the adjoint operators of the neural network. And we need it with respect to both the input of the neural network and the neural network parameters. And this is where it becomes a bit tricky in OOPS. All these operators has to be computed in the model core, which is implemented in Fortran. So we need a neural network library in Fortran, which provides all these operators. So we couldn't find one, actually, so we decided to go with our own neural network library. So we provided an implementation for only simple neural networks, but we did it. We implemented this library. We have implemented also the interface in OOPS to be able to use it for data assimilation experiments. Okay, so we have a new fancy methods where we are able to use neural network in data assimilation. But before we use it in operational conditions, so we want to test it using low-order models. So to do this, we will use the QG models, which is already implemented in OOPS. So this is a two-layer, two-dimensional quasi-geostrophic model. So in this model, the control variable contains all values of the stream function. So you have two levels, 40 longitude, 20 latitude. So you have in total 1,600 variables. And we are studying model error. So we need to introduce model error. So what we will do is we will have a reference setup. So this will be our true model, and we will have a perturbed setup in which we will change a bit the layer depths and the integration time steps in order to obtain a model error which is a bit non-trivial. So for illustration, this is the model. So the top two lines, top two rows, this is stream function for the top level, bottom level, 3 different snapshots, 2 days between each snapshot. And what I show here at the bottom line, this is the model error, W, top level, bottom level. So this is the model error when you start a 1-day forecast from this initial condition. And you see some patterns which are related to the state, but which are also non-trivial, for example, here. So this is exactly what we will want to predict with our neural network. Okay, we have the model, we have the model error. So now we want a neural network. So by construction, we know that our method is very similar to parameter estimation, which is known to be challenging when the number of parameters is high. So this is why we want a neural network which is as small as possible in number of parameters. So taking inspiration from what have been done, for example, with the IFS by Massimo and Patrick back a few years ago. So we will use a so-called vertical architecture. What we will actually do is we will provide to the network vertical profile of the control vector. So we provide the stream function, top level, bottom level, at a given latitude and longitude. So these are actually 4 numbers. And we expect the neural network to return the model error for the bottom level and top level at this specific latitude and longitude. And now if we want the full model error field, we just have to iterate over all possible latitude and longitude. So this is a very compact architecture, which in our case has only 386 parameters, so a lot less than the control vector. So now we are ready to train. Before we jump directly to online training, we will do first offline training to provide a baseline that hopefully we will be able to beat. So since we want to train with sparse and noisy observation, we need to use a combination of data assimilation and machine learning. So effectively, what we use is we use data assimilation to estimate from the observation, we estimate the analysis. And then once we have the analysis, we use machine learning to estimate the model error correction. So in practice, since we want to do model error correction, in this framework, we will have to train our neural network to predict a quantity which is called the analysis increments. And in our case, these analysis increments are used as a proxy for model error. So now we will evaluate the accuracy of the corrected model using data assimilation experiments. Of course, if you predict the increment, you predict the model error for a one window forecast. But if we want to do data assimilation, you need to include the neural network correction in the model. So you need a one-time step model error correction. So you have to rescale it. And we will use a constant forcing. We will use this rescaled model error correction as a constant forcing in order to be consistent with what we have done in online learning. So in this table, I report the result, first guess root mean square error and analysis root mean square error compared to the truth. So this is strong constraint for DIVA without model error correction. Our offline neural network model error correction, and this is for reference weak constraint for DIVA. So the good thing that we can see here is if you look at the numbers, the neural network correction is effective and reduces both analysis and even more first guess errors a lot. Now, this is for the short-term accuracy of the model, but now we also want to evaluate the long-term accuracy. So in order to do that, after each analysis, we will do, let's say, long-range forecast, where we will update the neural network correction every day. And we will measure the forecast root mean square error compared to the truth as a function of the lead times in days. So you have the same algorithm. In blue, no correction. In green, our offline computed correction. And in red, this is weak constraint for DIVA. And this figure is actually very positive and shows that we get an effective correction where we reduce the error a lot up to, let's say, 10 to 15 days. OK, so we are now ready to actually start online learning with our new neural network for DIVA variant. So what we will actually do is we will use the parameters that we have obtained using offline learning. So we will use offline learning as a pre-training step for online learning. And remember, I told you we need a parameter error term in our cost function, for which we need to define a parameter background error covariance matrix for model parameters. So without further knowledge, we will use a diagonal matrix, and with the coefficients that we choose on empirical grounds. So we have tested several values, and we ended up with this one, which is for our model the best one. And this value is actually very important because it measures how much information we will transfer about the neural network parameters from one data assimilation window to the next window. And so we will run sort of long experiments, and as previously, we will measure the first guess, analysis, and forecast errors. So these are the results for analysis and first guess errors. Same colors as before, and the new neural network variant is in teal, in cyan here. At the start of the experiment, so we are very close to offline learning, and this is expected because we start with the same values for the model parameters. But this is time in days or in number of windows. And as time evolves, observations are available, and online learning starts to really improve the model, so which results in more accurate analysis and also more accurate first guess. And now, if we want to look at the long-range errors, so we will actually compute the forecast at the start of the experiments once the model has been trained offline for a sufficient time. And this is what we get. Same figure as previously, same colors, and the new variant is in teal once again. And this is positive in the short range for the short range errors. So the online trained model is more accurate than the offline one up to day 12. And then after day 12, we see that the error increase sort of accelerates. And we actually we suspect that this increase is related to the fact that we have chosen a very small neural network. Remember, only less than 400 parameters. So with this neural network, we are unable to have a model error correction, which is good for short-term and long-term errors. Okay, so quick recap of this first set of experiments. So we have developed a new variant of neural network for D-VAR, which can be used to perform a joint online estimation of the system of the state of the system and the neural network parameters. This new method is built on top of weak constraint for D-VAR and is implemented in OOPS. And we have tested it using the QG model in OOPS. It gives promising results. If you want to know more, you can have a look at our preprint. But now we estimate that this method is ready to be used for more realistic setup. And this is what I would like to show you in the next few minutes. So in this second series of experiments, our goal is to develop a model error correction for the operational IFS. So following what we have done with the QG model, we will use a two-step process. First, offline learning in order to screen some potential architectures for our neural network, and then to pre-train it. And then in a second step, we'll use online learning to evaluate our model in data assimilation and forecast experiments. So offline learning will be based on what has been done previously by Massimo and Patrick. We will use the operational analysis produced by ECMWF during 2017 and 2020. And once again, we will use the neural network to predict the analysis increments. But this time they are available every 12 hours. So we split our data into training and validation. We will use 2017 to October 2020 as training. So this covers IFS cycles 43R1 to 47R1. And for validation, we use the last year of our data, which is October 2020 to October 2021 with these IFS cycles. In this data, we will focus on the large-scale model errors. So we will use a low spectral resolution. So for example, here I show the T21 temperature increment at ground level. And what we actually do is we interpolate this low resolution data in a Gaussian grid with 32 latitudes and 63 longitudes. So this grid is actually slightly oversampled for the T21 resolution, but that's okay. It would give us a bit more training data. So now about the neural network architecture. So following what has already been done, we will split our variables into two groups. So we will use in one group temperature and logarithm of surface pressure. And in the other group, we will use vorticity and divergence. And we will keep the same vertical architecture. So this is similar to what we have done in the QG model. And I show here the example of temperature and logarithm of surface pressure. So we feed the neural network with one vertical profile of the atmosphere. So you see temperature for model level 1 to 137 and logarithm of surface pressure. And this time we give 4 additional extra predictors, so latitude and longitude, and additionally time of the day and months of the year. So time of the day to account for the fact that now we have increments every 12 hours, so we have a daily variability, and months of the year to account for the seasonality. Within this set of experiments, the advantage of this, let's say, column architecture is that the neural network that we develop can be used with any grid, no matter what Gaussian grid or any other grid that we use. And the total number of parameters that we get is relatively small, so of the order of 70K. So this is small, at least when you compare to the dimension of the control vector. But of course, this is not perfect, so you will lose information about the spatial dependency. But okay, that's the price to pay for using this architecture. So we have trained this network using standard deep learning tools. And I will show in the next few slides some results. So first, offline learning results. So this, in offline learning, my metric will be the relative mean square error. So this is the mean squared error of the model of the trained network over the validation data divided by the mean squared error of the zero prediction. So a score of 1 means that the correction brings nothing. A score of 0 means that you explain 100% of the increments. So overall the validation data, our neural network is able to predict, using this metric, 20% of the analysis increments. But then if you look into closer details, so this is the time series of relative mean square error. And then there is a strong signal that shows that overall the increments are more predictable in summer here than, let's say, in winter here. Okay, we can also repeat the exercise by looking at the prediction in space. So this is a vertical profile of relative mean square error, and this is a map of the relative mean square error. Both are average over the entire validation dataset, so over the entire validation year. And what you see here, except for a few upper levels, most of the improvement comes in the lower levels near the surface. And if you look at the map, there are specific regions where the neural network is able to improve, is able to predict the analysis increments, and other regions where it is not able to predict. Okay, that's it for offline learning. So now we have actually inserted this trained neural network into the IFS. So we have used more recent cycles for 48R1, and we have set up a few online experiments with our newly developed neural network for DIVA. And what I show here is a scorecard of neural network for DIVA compared to weak constraint for DIVA. So this is a 3-month experiment in winter 2020-2021. The scorecards, I focus on the comparison to observations. You have geopotential, temperature, winds, northern hemisphere, southern hemisphere, the tropics, vertical levels. And if you are blue, this means that our algorithm is better than, more accurate than weak constraint for DIVA. And if you are red, this means that weak constraint for DIVA is more accurate. So the positive thing is that we see a significant improvement in geopotential, especially in the southern hemisphere here. But however, the picture is not perfect because, as we can see in the winds, there is a degradation, for example, in the tropics. Okay, so this concludes my presentation. Please keep in mind that all these results I've shown with the IFS are still work in progress. There are many things that we would like to do in order to improve our methods. So we can, for example, try to improve the offline performance. We can play a bit with the neural network architecture. We can use a different resolution for the data. We can use additional extra predictors like land-sea mask. We would like also to improve the consistency between what we do in offline and online learning. More importantly, we would like to move to a time-dependent model error correction, within the window, because actually within the 12-hour window, there is we suspect that there is a variability, a temporal variability of the model error that we are actually at the moment unable to represent with our neural network. And finally, we also would like to freeze some layers of the neural network during online learning. So this is usually done in fine-tuning, where you freeze the first few layers of the network to focus on the last layers. And in our case, this could be very important because potentially it will mean that we will have less parameters to train. So we can imagine that we will be able to use larger neural networks, and larger means potentially more expressive neural networks. Okay, so that's it for my presentation, and thank you for your attention.
Yeah, thanks very much, Alban. Are there any questions? Any online? Okay. Well, I mean, I was wondering, so about the kind of technical limitations here. You talked about the possibility of maybe getting better results with larger neural networks and things. How close do you feel you are towards the limit of technical feasibility? Like, if you, like, do you think you could use much more complex models if you just had like more computing power or something? Or
in my opinion, the main limitation comes from the fact that we are at the moment we are limited to this vertical architecture, and this is due to computational capabilities. Because when you think of the IFS, the data is split over different processors, and the fact that we use this architecture, it is because we know that the entire vertical profile will be stored in the memory of one processor. And of course, this means that you cannot use spatial information in order to predict model error. So you lose something here. So yeah, if we could overcome this, this would be a major improvement, I think.
Okay, so it's like a parallelization issue.
Yeah.
Okay, great. Are there any other questions? If not, then yeah, thanks again to Alban, and move to the next speaker.